Hello everyone. Today I'm going to introduce our Iccv 2025 paper titled Met-to-Net, a Decoupled Two-Stage Spatio-Temporal Forecasting Model for Complex Meteorological Systems. Our goal is to make multivariable weather forecasting more consistent, more stable, and more accurate. I'll start with the motivation from data and method, then introduce our Met-to-Net framework, followed by results and conclusion. Meteorological variables such as temperature and cloud cover behave very differently in space and time, as shown here. Their data distributions and first-order differences vary significantly. When we train a single model to handle all these variables jointly, the heterogeneous patterns become mixed and misaligned. This leads to representation inconsistency and lower forecasting accuracy. So the first question we asked was, how can we make the model aware of each variable's unique dynamics? Beyond data inconsistency, another issue lies in the learning strategy. Conventional two-stage frameworks first reconstruct the data and then perform prediction. This shift in objectives creates a mismatch between the two stages, resulting in unstable optimization. As a result, the model may perform well in reconstruction, but fail to generalize during forecasting. To address this, we propose a decoupled but consistent training paradigm, Met-to-Net. Here is the overall architecture of Met-to-Net, the core of our approach. The model is trained through to alternating stages. In stage 1, each meteorological variable, for example, temperature, cloud cover, or wind speed, has its own encoder-decoder pair. These modules focus on capturing variable-specific spatial and temporal features without interference from others. Then comes stage 2, where the translator takes all the latent representations and fuses them into a shared space. This fusion allows the model to learn the cross-variable dependencies that exist in real meteorological systems. What connects these two stages is the momentum update mechanism shown here by the arrow in the figure. Instead of restarting from scratch, stage 2 receives a momentum-smoothed version of stage 1's parameters. This mechanism keeps both stages aligned, ensuring smooth optimization and preventing feature drift. By alternating between these two processes, Met-to-Net becomes decoupled yet coherent. Each stage focuses on its own task, but they evolve consistently. This design is the key to achieving stable and accurate multivariable forecasting. Here we show the quantitative comparison on the ERA5 dataset. Met-to-Net clearly outperforms WAST, Chao and Predarnan in all metrics, achieving lower May and MSE and higher correlation. Even as the forecasting horizon becomes longer, the error remains stable, demonstrating the robustness of our implicit two-stage design. These results verify that Met-to-Net delivers both accuracy and stability in multivariable forecasting. Beyond the weather data, we also evaluate Met-to-Net on general spatio-temporal prediction tasks. The results demonstrate that our framework generalizes well beyond meteorology, adapting to various datasets and motion patterns. This suggests that Met-to-Net captures not only variable-specific behavior, but also general spatio-temporal dependencies. It provides a unified way to learn both structured and dynamic processes. To better understand the stability of our model, we analyze both internal representation consistency and real-world prediction results. On the right, the CKA results show that our model maintains high consistency across layers, while tau fluctuates heavily between encoder and translator. This indicates that Met-to-Net keeps representations aligned during training. On the left, we compare typhoon trajectories for Mawar and Doksuri. The blue line, representing our method, stays much closer to the ground truth and forms a smoother path. Finally, the ablation results below confirm that the full model with implicit two-stage learning achieves the lowest error across all variables, proving that stable representation alignment leads directly to better forecasting. To conclude, Met2Net introduces an implicit two-stage training framework for multivariable forecasting. It effectively bridges reconstruction and prediction, achieving consistent and stable representations across both spatial and temporal domains. Our experiments show significant improvements in accuracy and long-term stability on Iccv and other benchmarks. Looking ahead, we plan to extend Met2Net to larger scale assimilation systems and incorporate more meteorological variables. We also aim to explore physics-informed constraints to further enhance model interpretability. That concludes my presentation of Met2Net. Thank you for watching. You can find more details in our paper, and all code and datasets are available on our GitHub repository. We look forward to your feedback and collaboration. Thank you again.